Hello, welcome to this lecture. In the last lecture, we have defined torsion of a curve in R3. So in this lecture, we'll show that if torsion of a curve in R3, if it is equal to 0, so then that curve, it lies in a plane. And after that, so we'll give equations related to tangent vector, normal vector, binormal vector, and curvature and torsion of a curve in R3. So those equations are called Frenet-Serret formulas. Okay? Okay, so let us begin. Okay, so let us recall the formula we obtained for the torsion in the last lecture. So torsion. So let gamma be a regular curve in R3 with nowhere vanishing curvature. Okay, so then, so this torsion, so we got this thing. So torsion, so tau, so this is equal to gamma dot vector product with gamma double dot, and the whole thing is dot product with gamma triple dot divided by norm of this gamma dot with gamma double dot whole square, norm square. Okay, so here also we are taking this gamma to be a smooth curve also. All right, okay. So before going to show that torsion of a curve is 0 if and only if that curve lies in a plane, so let us compute torsion of a curve in R3 using this formula. So example, so let us take, so let gamma theta is equal to a cos theta, a sin theta, b theta. So gamma is a circular helix in R3. Okay, and so what is my gamma dot theta? So this is minus a sin theta, b a cos theta, b, and gamma double dot theta is minus a cos theta minus a sin theta, comma 0, gamma triple dot theta is equal to a sin theta minus a cos theta, comma 0. Okay, and now from this formula, so from this equation, so what you'll get is tau is equal to b by a square plus b square. Okay, so you'll get this thing. Okay. Okay, so here you can observe that. So if I take this b is equal to 0, so this implies that this gamma theta is a cos theta, a sin theta, comma 0. So gamma lies in this xy plane. Okay, and this B equals to 0, so this will also imply that this torsion is equal to 0, and torsion equals to 0, so this will also imply that B is equal to 0. Okay. Okay. So now in general, we prove this thing. So proposition. So let us take, so let gamma be a smooth regular curve in R3 such that gamma has nowhere vanishing curvature. Okay. So then the image of gamma or trace of gamma lies in a plane if and only if the torsion of gamma is equal to 0. If the torsion tau of gamma is equal to 0. Okay. So what is the proof of this? Okay. So in order to get the torsion of this curve gamma, so we have taken arc length reparameterization. So take arc length parameterization of gamma. Okay. So now note that, so changing the parameterization of a gamma, it does not change the image of gamma. So if gamma, if it lies in a plane, so it, and if you change the parameter, it will continue to lie in that plane. Okay. All right. So we have taken arc length parameterization of this gamma. Okay. So now first suppose that, so suppose image of gamma lies in a plane a1x plus a2y plus a3z equal to d. Okay, suppose this gamma lies in this plane. So this plane again you can write in this way. So a1, a2, a3. So you take this vector, dot product with this xyz vector. Okay, and now let us take, so let a is equal to this a1, a2, a3, and r is equal to x, y, z. Okay, so therefore this plane is nothing but a dot r is equal to t. Yeah, so this xyz is variable, so therefore this vector r is also a variable thing. Okay, so also we can take, so this a to be unit vector, so without loss of generality, we can assume a to be unit vector. Okay, so if it is not unit vector, so then divide the both sides of this equation by norm of A. Okay, all right. And so this gamma, it lies in this plane. So therefore what we have, so gamma lies on this gamma dot A is equal to T. Sorry, R dot A is equal to T. So this means that, so this gamma S dot product with A is equal to T. So for all S belonging to the domain of gamma. Okay, and now you take the derivative. So differentiate with respect to S. So therefore what we'll have, so gamma dot S dot product with A is equal to 0. So this gamma dot S, it is a tangent vector. So this tangent vector of this gamma dot product with A is equal to 0. Okay, and so next, so what we have, so this, so again, if I take the derivative of this, so then what you'll get, yeah. So if I take the derivative of this, again we'll get this is equal to 0. Okay, and but we know that this T dot S, so this is equal to Ks and S. So Ns is the unit normal vector. Okay, so therefore this Ns dot product with A is equal to 0. Okay, so maybe I'll just write down. So Ks Ns dot product with A is equal to 0. And now, so this Ks not equal to 0, so this will imply that so this dot product is equal to 0 for all S. Okay. Okay. So now, so both this tangent vector and this normal vector is orthogonal to A. So this dot product is equal to 0 and this dot product is also equal to 0. So this implies that this A is orthogonal to both this tangent vector and the normal vector. Okay. So now if I take this binormal vector Bs, so this is binormal vector Bs, so which is nothing but this tangent vector product with the normal vector. So if I take this thing, so because A is orthogonal to both the tangent vector and normal vector, and A is also unit vector, so A will be parallel to this binomial vector Bs. Okay, so this implies that so Bs equal to A or Bs equal to minus A for all S. Okay, so this binomial vectors, so it is now a constant vector. Okay, so this implies that so B dot S is equal to 0. Okay, so B dot S is equal to 0. So now, so what is the relation between the derivative of this binormal vector and the normal vector, it is given by this equation. So B dot S is equal to minus tau S times the unit normal vector. So this we have obtained in the last class. So B dot S is equal to 0. So therefore, this is equal to 0. N is unit normal vector, and this is true for all S. So this implies that this tau S is equal to 0 for all S. Okay, so we have shown that if the curve, if it lies in a plane, so then the torsion is equal to 0. Okay, and so conversely, so assume tau S equal to 0 for all S. Okay, so the torsion of this curve gamma is equal to 0 for all S. Okay, so now so you want to find a plane where this curve it will belong. Okay, all right. So because tau S is equal to 0, so again, so this B dot S, which is equal to minus TS times the unit normal vector, so this will be equal to 0. So this implies that, so this binormal vector, so B is a constant unit vector. So B is a constant unit vector, and so you know, if I okay, so what we want to show that so there exists a plane something like this, R dot B equals to D. So where this curve gamma it will belong. Okay, so you take this dot product. So gamma S, it is a point in R3, it is a vector. Take the vector dot product with the vector B. Okay, so if it is constant, so then this gamma it will lie in a plane. So in order to prove this is constant, so take the derivative of this. So which is nothing but gamma dot S dot product with B. B is a constant vector, so therefore we have this thing. And this is my tangent vector dot product with B. So the tangent vector is orthogonal to B, so therefore this is equal to 0. So therefore gamma S dot B is equal to D for some constant D. Okay, and this is true for all S. Okay, so therefore gamma S dot gamma, the curve gamma lies in the plane R dot B is equal to T. Okay, so therefore we have proved the proposition. And so next, let me state this Frenet-Serret equations. Frenet-Serret equations. So let us take, so let gamma be a unit speed curve in R3. and the curvature, it is not equal to 0. So gamma is a unit speed curve in R3 with nowhere vanishing curvature. Okay, so then so this following equations holds true, hold true. So t dot, so t is the unit tangent vector, so this is equal to kn. So k is the curvature. Okay, and if I take the derivative of the unit normal vector, so it will be minus k times the tangent vector plus tau b. Okay, so where this tau is the torsion of this gamma. And if I take the derivative of this binormal vector, so this will be equal to minus tau times the normal vector. So the first and third equation already we have seen, and also it is easy to show the second equation also. Okay, so note that so this normal vector is this vector product. Okay, and now you take the derivative. So if I take the derivative, so this will be equal to this. Okay, and b dot, already we know it is minus tau normal vector product with the tangent vector plus b vector product with k times this unit normal vector. Okay, okay, so so this thing is minus tau times yeah, so not minus, so tau of this minus of this n vector product with tau, so this will be equal to, yeah, okay, so maybe I just write like this, plus k vector product with b with n. So this is minus of this b plus k times minus of this unit tangent vector t. So therefore, so this will be equal to minus k t plus tau b. Okay, so we'll stop here. So in the next class, so what we'll see there, so if you have a curve in R3, so this torsion and this curvature, it determine the curve uniquely up to isometries of R3. Okay.